Go ahead. So,
oh, someone's hit record for me, have they? Already.
I think we're recording.
Can I just... progress. Yeah, we are. Okay, so someone's hit that for me. Righto.
So, okay, so before we start, I would like to acknowledge the Woiwurrung people of the Kulin Nation as traditional owners of these lands who have met and discussed science for several thousands of years. So it's a pleasure to have Professor Jennifer MacLeod with us. Professor MacLeod is currently the head of School of Chemistry and Physics at the Queensland Institute of Technology. Jennifer has given a talk a few years ago already here, so it's a pleasure to have her back and see what her group has been up to. She has a PhD in physics from Queen's University in Canada. She has further work at the INRS in Quebec, in Canada, and also in Italy at the University of Trieste. And Jennifer is an expert in surface science, and in particular in molecular reaction on surfaces, 2D materials, and spectroscopy and microscopy techniques. So today, Jennifer will talk about controlling the growth of molecular nanoarchitecture on surfaces. And yeah, I'm looking forward to that, Jennifer, and it's all yours.
Great, thank you, Augustine, and thank you for the invitation. I did speak a few years ago, and I think there's a little bit of overlap with what I talked about last time, but hopefully just enough to provide continuity for those of you that were there and not repetition. I missed an S in my title, Controlling the Growth of Molecular Nanostructures on Surfaces. Hopefully I can convince you that we've got a bit of control. That's the aim of the talk today. So I would also like to acknowledge the traditional owners of the land where the work that I'm going to show you was done. It's the Turrbal and the Yagara people. The lands were never ceded. I pay respect to their elders, lores, customs, and creation spirits, and acknowledge that where QUT has always been a place of teaching, research, and learning. And there it is. That's the location of QUT for those of you that haven't been here, don't plan to come this week, but we are located right there. This is the CBD of Brisbane, and we are located at the end of the peninsula where the CBD is located, next to the Botanic Gardens. It's a beautiful location, and some of it is even vibrationally stable, which means that we can do some pretty neat microscopy. For those of you that are looking for an excuse to visit, we're hosting the AIP summer meeting later this year. Optimistically, we are still planning for an in-person meeting in early December. So if you're interested, do check out the website. Abstract submission is open. Registration will be open soon. And we've got some really great speakers locked in already. So here's the group. The work I'm going to talk to you about today has really been driven by the students who you see in sort of the bottom half of this composite image that we put together last time we were in lockdown. So it's poignant. This was last year. We could put together a new one this week. The academic leads in this surface science and 2D materials team are myself and Josh Lipton-Duffin and Nunzio Mata and Dongchen Chi. And the students really drive the research. So you'll be seeing work from a selection of these students today. So what are we trying to do? I think it's conceptually interesting. I started putting together this talk and got a little wrapped up in thinking about the metaphors that we use for the type of work that we do, and in particular, the way we always refer to molecular building blocks, or at least I tend to refer to molecular building blocks. And I think it's a really nice visual metaphor. And what I was trying to sort of examine conceptually was how well that metaphor hangs together. When we think about sort of building blocks for babies, I mean, we think about nice wooden blocks like this and sort of a limited ability to make any complex architecture. And when you think about it, that actually relates to sort of the lack of directional interactions between these blocks. We rely on gravity to keep them together, which means we do have some constraints on how complex we can be in our aspirations for block related architectures. But if we switch up our blocks to something a little more sophisticated where we do have strong directional interactions, we get a lot better capability of making architectures that are interesting or functional. And so we can take our building blocks and we can really start to put together some rather beautiful objects. But the thing is, when we're working with these macroscopic building blocks, the key really is the we can put together part. The human interaction that's required here is massive. For those of you that have spent time with your kids or without kids, putting together Lego architectures, it takes a huge amount of human input to make them. And of course, when we're doing surface science, what we would prefer is to rely on thermodynamics to enable the assembly of systems for us. So if we continue with this metaphor, what we are conceptually trying to do here is to take a base plate, which of course for a surface scientist would be an atomically clean substrate. And we add to it our building blocks, our Lego box. And the idea would be that spontaneously we would get our desired outcome, some sort of complex or interesting architecture. And of course, macroscopically, this doesn't happen. The probability is vanishingly small that we can take this load of Lego blocks and throw them at our base plate and have them assemble this way. But of course, we can use judicious choices of our substrate and our molecules at the molecular level and come out with fairly predictable, robust outcomes that are actually very useful to us. And this is just a quick overview of one of the systems that's really a darling of people that work with molecules on surfaces. This is benzene 1,3,5 tricarboxylic acid or trimucic acid. And when we use a non-reactive substrate, we're able to take advantage of self-assembly to create a desirable outcome. So when we talk about self-assembly, this is Whiteside's definition of self-assembly as the spontaneous organization of objects through non-covalent interactions. And this happens at all length scales, but what we're interested in, of course, is interactions at the molecular scale, things like hydrogen bonding or halogen bonding, which will enable an organization to propagate through our molecular layer. We can also look at an approach where we start with a building block and then put it through some sort of reaction on a surface, but retain the ability for self-assembly. So in self-assembly, pure self-assembly, we really don't want our building blocks to change. So if we were working with trimucic acid, we would want that molecule to stay intact as it went through the self-assembly process. That's sort of the definition. It's not really about what we want. It's about the definition of self-assembly. But we can also look at a process where we change the building block on the surface and then allow that slightly modified building block to self-assemble. And of course, finally, we can look at allowing a reaction on the surface that leads to covalent bonding. Rather than these non-covalent interactions, we can allow for strong bonding to occur. Generally, what we're looking at in the surface science experiments of typically planar aromatic molecules is a carbon-carbon bond formation. So our building block in all cases can be identical. And this is a schematic building block. It's not meant to be a molecule, and any resemblance to trimucic acid is accidental. In pure self-assembly, the activated form of the molecule is skipped, essentially. We don't do anything to change the molecule before it will undergo these non-covalent interactions. We can also do this reaction then self-assembly approach, in which we will alter the molecule through some sort of surface confined reaction, and then it will undergo non-covalent interactions to assemble. And of course, we can also initiate covalent bonding following the activation of the molecule. So we end up then with different products. And here would be a typical self-assembled structure where the molecular building block has been retained intact. And here you see a self-assembled structure where instead of the original building block, we're now using a modified one, but non-covalent interactions to assemble it. And typically, this would be metal organic or organometallic interactions on the surface. So these blue dots would be representative of atoms. I'm just looking at my self-assembly is not very good. It's a little bit of a defect in there. For the covalent bonding, what we'll see then is this condensed architecture where we've formed carbon-carbon bonds typically to lock in the covalent structure. And this is really good from an electronic point of view. This will allow us to have fairly long conjugation lengths, that sort of thing, if we're looking at a conjugated system. What I haven't indicated here is how typically this also locks in defects for us. So we tend not to get the perfection out of this approach that we do out of self-assembly, where there's an intrinsic reversibility available to us. So today what I'm going to mostly focus on is monolayer materials, but I really wanted to make a connection to some of the work that we're doing with films, because we've taken some of these ideas that we've been working on at the monolayer and looked at how they can be propagated into thicker films. So the first step that we will talk about here is about this aspect of control, which is, I think, aspirational in many respects, but we do have an idea, at least, of how to take charge of some aspects of molecular behavior on surfaces. And what I'll be talking about today in general is using a combination of surface reactivity and temperature through annealing processes to give us some amount of control over the chemical state of the molecular building blocks that we're using. For the record, temperature is not a great way to precisely control the chemistry of molecules, and this is something that we've been spending quite a bit of time thinking about, are more precise ways to look at activating our molecular building blocks. But temperature is really easy, and it's widely studied, and we understand quite a bit about the kinetics of processes. So for us, it's a logical choice to pursue these activated building blocks. The surface reactivity, of course, we have an entire array of surfaces at our disposal as surface scientists. We are typically working in ultra-high vacuum, which means that we can buy single crystal substrates of whichever metal we're interested in, mostly. And we can clean them up in ultra-high vacuum to give us an atomically ordered and atomically flat surface on which to work. This means we can sort of dial up the reactivity. And I've created this sort of spectrum of reactivity here, which could be based on something like D-band center of mass, I think, based on intuition as well, for those of us that have used these surfaces in experiments. So we can move all the way from a non-reactive surface to a very reactive one. When we work on non-reactive surfaces, we enable self-assembly. So this is the intact building block, which will non-covalently interact with its neighbors in its intrinsic form. This is the one I showed you before. It's called trimesic acid, or 1,3,5-benzene tricarboxylic acid, and the non-covalent interactions it undergoes are hydrogen bonding interaction through the carboxylic groups. This carboxylic dimerization has a bond energy of something like 10 kilocal per mole per molecule. It's extremely directional. There's a very good matching here. So we can very easily predict the type of architecture that we will see out of a self-assembly of trimesic acid. Because we can work on non-reactive surfaces, it means that we don't need to be in ultra-high vacuum to observe this structure. And this image I'm showing you here was actually obtained at the solution-solid interface. So it's a very nice technique because we can implement it in a bunch of different situations. Interestingly, we can also look at reaction, then covalent bonding on inert surfaces for reactions where we don't need to catalyze the chemistry. And the prototypical example that I'll show you here is a polycondensation reaction. The molecular building block is 1,4-benzene diboronic acid, which we can deposit onto graphite or graphene, and we heat it to about 100 degrees or so. And what you can see is that the boronic acids lose essentially water molecules. The molecular byproduct here is water, and this condenses our linear molecule into almost exactly the same architecture that we saw from TMA. So for those of you that are familiar with this chemistry, you'll know that this is actually the basis of the first observed covalent organic framework, which means it's got the very auspicious name of COF1. So this was reported in 2005 by Yagi and collaborators, and it essentially opened the field of covalent organic frameworks, which along with metal organic frameworks and zeolites are a really interesting type of material with persistent porosity. So those are the three sort of classes of materials that have this persistent porosity, which means they're great at doing things like storing gases or sieving gases if we want to do some sort of filtration of gases, this sort of thing. So COFs are generally synthesized into this crystalline form, something like a powder that you can see here in the SEM image. They are highly crystalline. The XRD shows you that. And typically we can confirm the presence of those baroxene rings that are formed after the condensation reaction through the use of infrared spectroscopy. So we've been looking at these not just in the monolayers that I showed you, but also trying to propagate that layer thickness upwards. And this is Nika, who is a PhD student who's been engaged in this work. We initially started out in Nika's project looking to make very sort of moderate thickness layers, which of course for a surface scientist meant we were going for about 10 layers or so. But we quickly figured out it was much easier to study them when we made them thicker. That 10-layer thickness is actually an intermediate place where it's a bit tricky to use some of our surface science tools to investigate the materials, and we did a lot better when we moved to thicker films. So Nick has actually been working on this now for a while, and what she's come up with is a really nice approach to creating self-supporting COF membranes, and these only contain the 1,4-benzene diboronic acid. There are no additional molecular binders in there. So she's able to synthesize these membranes, which, as we show in the paper that I cite here, they are chemically COF. There's a bit of, our conversion efficiency isn't 100%. It's quite interesting to work on this. When you're working on a bulk synthesis, you just wash away the stuff that you don't want. But when you make it into a membrane, you tend to lock it in. But these turn out to be really interesting from a bunch of different standpoints. We're able to measure the mechanical properties of these membranes using nanoindentation, which is kind of an information gap that's existed in COF studies for a while, because it is fairly difficult to synthesize them in a form which is amenable to these types of mechanical measurements. She's worked on scale up. There's no scale bar here, but I think this is a 4-inch watch glass that she's, apologies for the imperial, that she's synthesized this in. So you can see we're up to sort of tens of square centimeters of membrane size. It's a really interesting project to watch grow and develop. And what she's working on now is a mechanistic understanding of exactly what's driving the film's synthesis, which requires a very delicate balance here of sort of the solvent properties and the substrate properties. So it's a lot of surface science. If we're interested in other types of covalent chemistry, so not this dynamic covalent chemistry that can be reversed under humid conditions the way we use in the COFs, we can look at catalyzed reactions, for example, on copper or nickel surfaces. So this again is an example of a reaction, then covalent bonding type approach. And it's one we've been working on for years. This is some work I did at INRS in Montreal, where we took a very, very small fragment of graphene and converted it into larger fragments of graphene. This, in fact, though, did take a chemical reaction. What we did here was to convert pentacene into graphene on two different substrates, either on nickel 111 or copper 111, where you see the moire pattern associated with the graphene growth. What you'll notice, of course, is the very different reaction temperatures for the highly catalytic nickel surface versus the moderately catalytic copper surface. In both cases, what we were needing to do here was CH bond breaking and then carbon-carbon bond formation between these activated fragments. And so this is very sort of emblematic of the type of work that we want to be able to do. Take a building block and be able to lock it together like this into an extended covalent structure. However, it was pretty imprecise, I would have to say. And we, of course, started out with something that was a fragment of graphene. So one of the questions we've been looking at over the past few years is how precisely we can control things. And of course, one of the easy ways to get a little better control over a reaction is to reduce the reactivity of the surface on which we're working. So silver turns out to be a great surface for most things that we want to do. And the work I'll tell you about next is again based on the same molecule. As physicists, we're not terribly adventurous in our molecules in general, and we really like to stick with things that we understand well, and trimesic acid definitely falls into that category. So in this work, what we were interested in doing was controlling the deprotonation of trimesic acid. So the carboxylic groups on trimesic acid have, I'm seeing if I can find, there we go, have these very nice OH bonds, which we can break quite easily. Sorry, I'm getting distracted by my capabilities here on PowerPoint, which we can break quite easily on a reactive surface by injecting a little bit of heat. So what we were interested in doing was gaining some control over our ability to remove these one at a time, or at least more slowly than we would have, for example, in the CH bond breaking that I showed you on our pentacene molecules. So this is a reaction which falls into this category, where we're interested in allowing a reaction at our molecular building block and then inducing a self-assembly process. And we knew that this would be possible because there had been some previous work done. We start at the beginning, though, looking at trimesic acid deposited onto silver 111 at room temperature, where we observed the formation of the same chicken wire structure that we had seen previously on graphite under a number of conditions. So we weren't the first to observe this. This was an expected result. What it does allow me to show you, though, is that there's a very clear spectral signature of this molecule in X-ray photoelectron spectroscopy. In particular, the carbon 1s core level contains information about the central sp2 hybridized carbon ring, so that's the benzene, at the center of the molecule, and it also contains information about the functional groups. When we have intact carboxylic acid, it appears at a binding energy about 4.1 electron volts above that primary peak. This allows us to use XPS to measure the chemical state of the molecule precisely. So our intact molecule does exactly what we would expect and dimerically bonds into the chicken wire structure. We knew based on prior work from Kern's group that if we annealed the surface a bit, we should be able to partially deprotonate the molecule, leading to a condensed phase which is held together through ionic hydrogen bonding. And in fact, that's precisely what we saw. So following annealing at 155 degrees Celsius, XPS tells us that the molecular overlayer is about 25% deprotonated, which leads to this condensed ionically hydrogen bonded phase. So reacted, then self-assembled. What we did was to keep going with the annealing experiments, and we produced some rather beautiful phases doing this. After annealing to 200 degrees Celsius, we produced this non-periodic phase where we have central bright protrusions which are surrounded by 6 roughly triangular features. And what you'll notice is those are either isolated, where they appear a little bit like flowers, or they're knitted together so that they share triangular features with their neighbors. This was really interesting to us. It wasn't necessarily what we expected. We hadn't seen it before. The triangular features definitely look like the trimucic acid molecule, and the bright features we anticipated were silver add atoms, because that's the first thing anyone would guess in this situation, given a bit of a history in surface science. When we annealed higher to about 220 degrees Celsius, we were able to completely condense the phase such that all of the triangular features were shared between 3 of these bright protrusions. So we call this the knitted pinwheel phase, because these pinwheels are now all knitted together. And in fact, we were able to do XPS repeatedly in order to get a handle on what was happening here. We followed this chemistry through a few times before we entirely figured out what was going on. What we determined was that we had begun to deprotonate the molecule after the annealing to 155 degrees with the ionic hydrogen bonded phase. This shows up as a second spectral contribution in between the carboxylic contribution and the primary peak. So this growth of a second peak, which is about 3.5, little more, 3.8 electron volts above the primary peak, corresponds to the formation of carboxylate, COO minus. So this is our deprotonated segment of the molecule. And what we were able to do was to observe that the non-periodic phase had a deprotonation somewhere between 25% and about 75%, and that when it was 100% deprotonated, we formed only the knitted pinwheel phase. The schematic at left here shows you the combinations of bonding that are involved in these structures, where when we have discrete pinwheels, we actually identify that there is very likely a cyclic hydrogen bonding going on in the portion of the molecules which still retain their carboxylic groups, and that there is a cyclic bonding of the carboxylates around the bright features in the other part of the molecule. Absolutely fascinating. So we move then from XPS at 50% deprotonated, giving us our discrete pinwheels, all the way to 100% deprotonated, where we see the knitted phase. And in between, we see this non-periodic phase, which contains both discrete and knitted pinwheel contributions. The entire thing is also chiral. It's an absolutely fascinating set of attributes of this overlayer. The TMA molecules are actually slightly rotated with respect to the unit cells that we can define within this structure. As it turned out, when we did a little more vigorous dig through the literature, we actually did find that this had been observed before. What you can see here is that it appeared in a master's thesis, which was published in 2013, which presents, unfortunately, only just an observation of the phase. I mean, fortunately, unfortunately, I'm sure the students were really delighted to have found this. But as you can read at the bottom of the page, they found it very late in the work, and they weren't able to analyze it. So we were able to provide some insight based on the fact that our microscopy was combined with the XPS, which allowed us to comment on the chemical state of the molecule and to better understand what was going on. So actually, immediately sort of after we published it, we realized that they were still working on it in Denmark, because very quickly after our publication came out this really nice theoretical paper where they demonstrated that the center bright protrusion in this network actually comprises 7 silver add atoms. 6 of them bear the same oxidation state, and the one at the center is slightly different. It's a really fascinating set of results reported in this paper. This is not a logical next question, but it's one that we ended up investigating for slightly different reasons. We ended up doing some work looking at what would happen if we tried to replicate some of these experiments on silicon. Led us to this question of, can we move away from single crystal substrates? The answer turns out to be yes, and it wasn't, like I said, a question that we set out to answer, but it's one that Vishakya ended up finding a bit by accident. She was attempting to work on the silver root 3 by root 3 reconstruction on silicon 111. Of course, silicon is intrinsically way too reactive to do any sort of molecular self-assembly or even covalent bonding work, simply because molecules tend to fall apart and bond to the silicon substrate very quickly. We get a lot of sort of dissociative adsorption going on this highly reactive surface. So Vishakya was working to reduce the reactivity of the silicon by terminating it with a silver monolayer, creating a root 3 by root 3 reconstruction, which you see at the top of the slide here. Turned out not to be great for our molecular reaction experiments, but what she did find was that if she increased the coverage of silver, she was able to grow tiny little micro islands on the surface that turned out to be themselves very small single crystals. And these grew both in a 111 orientation and a 100 orientation. You can see here STM images both of sort of macro scale features of those islands, as well as the atomic resolution. We further confirmed this with X-ray diffraction off of the surfaces. So depending on her growth conditions, she could either grow a predominantly 111 oriented set of islands or 100, or she could have a mixture of both 111 and 100 oriented islands on the same silicon surface. So as we are wont to do, we then covered them with molecules. And as it turns out, they behave identically to the large single crystal substrates that we had been working on. So this is interesting. It's a whole new approach to doing growth experiments rather than sputtering and annealing a single crystal. You can do a simple flash annealing of silicon with the deposition of silver, and you end up with a beautifully ordered set of silver crystallites to work on. So you can see here she was able to reproduce the same TMA work that we just looked at from a single crystal surface, and at the same time was able to study what the molecule does on the 100 facets. And here there's less in the literature, so she also reproduced these experiments on a 100 single crystal. So this was really kind of a neat bit of work, and we're still trying to figure out exactly what we can do with it. But it's, I think, a beautiful demonstration of the types of innovations that we accidentally run into as surface scientists. Vishakya created some very beautiful art to go along with this, and here you can see her Blender rendering of both the 111 and 100 islands. So covalent coupling. We looked there, of course, at the control of reaction, then self-assembly. And of course, another ethos we can use is to pursue covalent coupling. And this is Yolanda's work, and Yolanda's watching, so I hope I do a good job of relating it. Yolanda worked on this molecule here, which is dichloroethylene dioxythiophene, which is dichloro-E dot. If we successfully polymerize it, we produce a well-known organic polymer called P dot. This happens through a process called Ullmann dehalogenation, which is schematically represented at the right of the slide here, where what we're interested in doing is breaking a carbon halogen bond, which will then allow the formation of an organometallic, which can then be converted to a covalent polymer. The tricky bit is getting through that conversion of the organometallic to the covalent polymer. And that's because there does tend to intrinsically be a pretty high barrier to that conversion. So we run the risk of either desorbing our molecular precursors, or in the case of this very sort of Baroque molecule, of breaking it because it's full of heteroatoms. So here we're pursuing reaction, then covalent bonding, but the difficulty is we need to find a surface which is reactive enough to dechlorinate the molecule, but not break any of these carbon heteroatom bonds. So we need a surface which is reactive, but not too reactive, and we need to find the correct reaction temperature. This work was done at the synchrotron to do sort of high throughput screening of the different substrates. at our disposal, and also because X-ray photoelectron spectroscopy, or photoelectron spectroscopy more specifically, is the perfect tool for looking at this molecule. It's got a rich array of heteroatoms, a bunch of core levels we could look at, but as it turns out, carbon 1s contains all of the information we need to see whether the molecule is intact. So working on copper, and this is where I'll start going quickly because I think this was part of my talk last time I was at Monash. Working on copper, immediately upon deposition, we see the green peak, which is indicative of broken molecule. And so even without heating, already we know the substrate's too reactive. Adding temperature only makes it worse. The molecule is irrevocably broken. This is not the substrate we were looking for. On gold, we find a different problem. The rising background shows you how difficult it was to stick the molecule to the substrate. We get an organometallic at room temperature. Things continue to look okay with moderate heating, but the molecule breaks. And heating it more does not convert the organometallic to a covalent polymer, but instead leads to a broken molecule. So silver was our last ditch effort, and disappointingly, the molecule didn't even stick to it. But we could, in fact, stick the molecule to the surface when it was heated. So at 150 degrees, we get a nice dissociative adsorption where the molecule breaks enough that it doesn't desorb off the surface again. And as it turns out, that breaking was the carbon-chlorine bonds. We're able to form both an organometallic and a covalent polymer after deposition at 150. The molecule starts to break with additional heating, but we have now the recipe that we needed to make the polymer. They did near-edge X-ray absorption fine structure NEXAF spectroscopy on the surface to confirm that the molecule was lying flat on the surface. So this was good. It's the orientation we wanted because the outcome that we were looking for here was this flat polymer. When we took the molecule home and did the same experiments in our STM system, we were able to observe that everything we had measured at the synchrotron indicated the polymer we created was the one we wanted, and our STM confirmed that. This flat-lying polymer then, of course, has the benefit of extremely long conjugation lengths along its backbone. Our DFT here with Tursoff-Hammond simulations really matches our STM images. So we have overall a very good indication that we did what we set out to do in terms of matching the reactivity with the reaction that we wanted to achieve. But interestingly, one of the things that didn't bother us in this experiment was the byproducts. The removal of these halogen atoms tends to actually be fairly problematic in Ullmann dehalogenation reactions, and that's because they stick around and act as a poison to the catalyst. They're retained on the surface and they block the active sites on the surface. So one of the things we've also been interested in is whether we can mitigate this effect. We've done work to avoid it by working with other reactions, but if we're interested in doing Ullmann dehalogenation, this really seems to be unavoidable. And here you see a couple of works on Ullmann dehalogenation that show just how prevalent it is. Retained halogens are really commonly observed as interstitials between the polymers or the organometallics that are produced through this process. So here's our reactive surface where we're looking to retain the byproduct and then see if we can remove it with a post-treatment. So reaction, then covalent bonding process. And this is the molecule that we were working with. It's very simple, 1,4-dibromobenzene, which will polymerize after covalent bonding into polyparaphenylene. The image, there's some wingdings in there, but the image shows you an organometallic structure labeled as such with interstitial bromine atoms between the organometallic rows. And it also shows you what the covalent product looks like. And that's where the wingdings are not labeling it at all. What you'll notice is that there's change in epitaxy between the organometallic and the covalent product. And that's because, of course, they have a different periodicity. So the epitaxial matching is along different substrate directions. So here we're looking to remove that bromine from between the lines. And we had an idea of how we could do this based on work from Mikey Storr's group, where she had shown that molecular hydrogen can reduce the prevalence of retained halogens on the surface. We went one step further and we used atomic hydrogen from our hydrogen cracker that we happen to have in our system. So what we did was to just spray it at the surface and to watch the bromine 3p core level disappear. You'll notice in carbon 1s, there's really not a big difference, but we're able to remove all of the bromine from the surface. In terms of what it looks like to STM, here it is. Our as-grown polymers are beautiful. You see them here at different spatial scales. In the 15 by 15, you can definitely see the halogens decorating the edges. After the hydrogen exposure, they actually look pretty terrible. So our spectroscopy looks good here. Our microscopy does not. But with a short anneal, we're actually able to restore the ordering really nicely. We see slight changes in epitaxy, and we definitely don't see the halogens retained around the edges of the polymer. So this is where we take another little foray into a slightly different direction. What if the byproduct could become the product? This is work that's being done, again, in a film growth sort of way. And this is Hugo Hartl, who's been working with atmospheric pressure cold plasma for a few years now. What's shown here at right is a dielectric barrier discharge plasma apparatus, and the purple part there is the plasma. So we're interested here in the same reaction, Ullmann dehalogenation. And what we've been working with is a liquid at room temperature molecule. This is 1,2,4-trichlorobenzene. And what Hugo does is to put it in a droplet onto a surface and then to put it into the dielectric barrier discharge plasma. So the side view that you're looking at there is actually just the liquid droplet of the trichlorobenzene on our substrate. So the work that Hugo did started out with films. So we deposited films onto silicon and then looked at treatment with plasma to see whether we could achieve dehalogenation. We could. As it turned out, the dielectric barrier discharge plasma created this liquid to solid conversion, so we could visually see that the reaction was progressing. What you're seeing at right here, these are optical profilometer images that show you the types of structures that emerged after different treatment doses, essentially, in the dielectric barrier discharge plasma. The center ones are perhaps most representative. We get these sort of spinodal features, absolutely stunning at different length scales. And what's shown to you here in the XPS data, which don't actually look like XPS data, this is just the quantification showing you that our chlorine to carbon ratio drops significantly through this process. And we interpret this, of course, as a dehalogenation reaction where the plasma has assisted dehalogenation of these molecules at the reactive metal surfaces. We cannot reproduce this result without a metal substrate, which is why we think it's plasma-assisted dehalogenation. Interestingly, though, we started to expand the work to look at molecules that had some different halogens on them and to look at a different substrate. We also moved to a different plasma apparatus, so there were a few perturbations here, but Hugo started very repeatedly seeing crystalline products, which we had never observed before. The dehalogenation should have led to a heavily cross-linked organic polymer, and this is what we measured using TOF SIMS and a few different techniques, was essentially that we had created sort of a dense carbon-based polymer mesh. When we started getting crystalline products, we really didn't know what was happening. As it turns out, what we were doing was facilitating the synthesis of cuprous halide nanoparticles through this process. So our dehalogenation byproducts, the chlorines, the bromines, the iodines, you'll notice we're using a whole selection of molecules now, we're reacting with the substrate to allow the synthesis of these nanoparticles. These are really interesting materials, the 1,7 semiconductors. These cuprous halides are transparent p-type semiconducting materials that have a lot of really interesting intrinsic properties. So it was a real treat to find such a fast and easy way to synthesize them. So they come out as part of a composite film here. You can see, though, that we can confirm their presence with X-ray diffraction. We also see the expected excitons from these nanoparticles. And at left, you'll see that they invited us to submit cover art, and I don't think it's going to make the cover, so this is your opportunity to see it. There's our plasma factory for making these nanocrystals. Not completely related, but Hugo is also working on extending this particular approach to making coatings on mild steel. And as it turns out, ultrahydrophobic coatings on mild steel come out really nicely. I'm not sure if this is an ultrahydrophobic contact angle or not, but it can be. And they're really good for corrosion protection. So it's an interesting approach to film synthesis. So just very quickly before I finish, we are interested in particular targeting electronic properties in these materials. And we've been measuring that in a conventional way in our system, looking at figuring out what the density of states looks like for these materials. When we're looking at filled states, we do that through ultraviolet photoelectron spectroscopy, just schematically illustrated there for you. That's a photon in, electron out technique where we're able to map the filled states. And of course, we've also been working on the development of an inverse photoemission spectrometer, which is an electron in, photon out technique where we're able to map the unfilled states. This is what the instrument looks like schematically. Our electron gun is Stoffel-Johnson type. We've had a lot of trouble with our cathodes, and we've ended up with a Lab 6 source in there, which gives us a ton of electrons and maybe a little worse energy resolution than we would like. Our detector is either a Geiger-Muller type, as shown schematically here, where we do vacuum UV detection inside the chamber. So these are the photons emitted after the inverse photoemission spectroscopy process. We can also detect in the visible outside the chamber. And that's really nice because we're able then to use lower energy electrons to do our probing, which should probably cause less damage to organic materials. And we're still working on quantifying that. There's Gabriele installing the system. He's doing a little work there on the Geiger-Muller detector. And this is one of our other PhD students, Steve, who's been working on some fullerene films, which it turned out give us really beautiful density of states information that we can map through this combination of techniques. So this is an incredibly crowded diagram, but it gives you a real example of what we're able to measure using this approach. We get an energy referenced measurement of our frontier orbitals where we are able to measure our conduction gap, we are able to measure the electron affinity, and we can identify those with energy referencing to the vacuum level and Fermi level. Just one more note about those C60 films. Steve's actually working on those to look at them as a basis for another approach to non-graphene layers. I say non-graphene because Steve's work is in looking at intrinsically defective layers. We're really interested in how much crystallinity contributes to the electronic properties we see. Our intuition says not much, so we're interested in looking at whether we can actually control the level of defectiveness or disorder in a film and measure the effect that that has on these electronic properties. So in summary, there are a number of different ways for molecules to interact and organize on a surface, and that's what we're interested in studying. We're using surface reactivity and temperature, plasma to induce reactions. We're interested in the byproducts, whether we need to tolerate them, whether we need to remove them, or whether we can do some sort of process where the byproducts actually become useful to us. We do all of this, of course, with surface science instruments. So thank you very much for your attention, and of course, huge thanks to everybody that contributed to this work.
Thank you, Jennifer, for
You're welcome.
Beautiful talk and beautiful set of techniques. Very diverse and very complementary. So I have a lot of questions, but maybe anybody from the audience has any question for Jennifer? I don't see.
I have a question, Augustine. Hi, Jennifer.
Hi, Dave.
Hello.
Hello. I'm sorry if I missed this because I was trying to do some homeschooling at the same time as watching your seminar, but it seems that you're able to do XPS and STM in the same chamber. Is that right?
Yeah, absolutely. I forgot to mention that. I should have shown a picture of the setup. Our system has XPS, which has both the X-ray and the ultraviolet source. It's an SPM, so we can do either STM or AFM on our scanning probe instrument. And we've also got our inverse photoemission spectrometer in there, as well as spot profile analyzing lead. So we can do a range of things.
Oh, it's very nice. It's nice to see the XPS alongside the microscopy.
Yeah, it's really useful. It's the single most frustrating thing about STM is not being able to directly determine which atom you're looking at. So it's nice at least to have the surface averaged chemistry to act as a guide to figuring out what we're looking at.
Thanks.
Any other question for Jennifer from the audience? So, Jennifer, maybe I have a question regarding those silver 7 clusters.
Yes.
So, what's their electronic configuration? Do you know?
You're going to have to go to the theory paper to get that. It is really interesting, though, because there does seem to be sort of this ring of the silver add atoms that are interacting with the carboxylate, which of course puts them into a different oxidation state than that one atom that's protected at the center. So we end up with 2 separate oxidation states for the different members of the silver 7 cluster.
Is there any chance there's some interesting magnetism there? For example, some partially empty D bands of silver?
That's a really good question. And as far as I recall, the paper that came out of Denmark didn't do any investigations of that. So I think it may remain an open question, but certainly one that could be addressed through density functional theory based on these already resolved models that they've got, or already accepted models, I guess, that they've made for the structure.
I see. And yeah, another question I have is regarding that the COFs and their catalytically driven synthesis. Is there, or do you have any vision for, benefiting from that catalytic activity from, let's say, nickel or even copper, but let's say with a cheaper, lower quality foil, for example, that then we could etch and just keep a single layer of COF? Is that something that...
Yeah, I mean, entirely possible, and certainly something when you look at any of the scale-up work around this on-surface chemistry, it tends to be predicated on using an etchable film rather than a single crystal substrate. For the COFs in particular, in fact, it's not a catalyzed reaction. That dynamic covalent chemistry progresses with temperature. So getting a single layer of the COFs is actually pretty straightforward. The difficulty with the boronic acid chemistry is that you can rehydrate those bonds really, really easily. So they're not very robust with respect to atmosphere. So the difficulty there is just having the handling conditions under which the COF will persist. And of course, it's not a huge problem. You can certainly do it with anhydrous solvents and that kind of thing. The single layer of the COF, though, what do you think that would be interesting for? It's an interesting question.
From the angle of electronics, I think that could be, I mean, if you, let's say, design an approach to have large-scale single layer of COFs, you can and etch out the metal and even transfer it onto a dielectric.
Yeah, they themselves are pretty. They're insulating essentially. There's different theoretical works on the gap associated with COF1, and depending on the DFT you use, it's anywhere between like 4 and 7 electron volts. So they themselves are. Anyway, they're a really interesting material, and I certainly don't think that there's anything that would stop you from growing it directly on a dielectric, as long as it I mean, I guess actually molecular orientation during the synthesis might if the molecules don't want to lie flat. But you can also exfoliate. You can do a bulk synthesis of these coughs and then exfoliate them the same way you do with graphene. So the potential to transfer them is certainly available. I don't think you necessarily need to start with a monolayer to look at transfer.
Yeah, so I just maybe a last question. So, and do you see any possibility of engineering that gap by, let's say, having precursors with a larger size delocalized electron group?
Yep. Yeah, absolutely. That's one of the #1 pursuits in cough research, is looking at different functionalities. So it's essentially a modular approach of these sort of struts and nodes that you put together in a systematic way through dynamic covalent chemistry. And so a lot of the work right now is in engineering materials that have interesting functional properties. So yeah, you're certainly not limited only to the boronic acid chemistry within coughs, and you're certainly not limited only to the benzene rings as your organic struts. So there's been a lot of work done to look at coughs with different properties. The dynamic covalent chemistry does tend to be uncatalyzed, so I think it's a really interesting class of materials to look at, particularly for working on non-metallic substrates. Okay,
yeah, Jennifer, yeah, thanks. I'm sure we could keep talking about this.
Probably.
Beyond the scope of this meeting. So anybody else has any question for Jennifer before we let her go? Okay, I think everybody's slowly getting, saturated with the Zoom.
Yeah, no kidding.
So Jennifer, thanks again for a very nice talk. And
you're very welcome.
Hopefully next time we'll have you in person. And,
that would be great.
And that we can travel also to QT.
Yeah, that'll be a few days anyway.
Yeah, okay, well, all the best up there with the current situation. And
yes, thank you very much.
We'll be in touch.
Good.